I lost somebody, at least one, maybe two. I must be going too fast. Okay, so the last item I want to talk about a little bit, and again, an hour is not going to really give it justice, but I'm going to try to introduce you into it, is continuously welded rail and track buckling. Now, I believe I already showed I showed you the movies earlier, so I'm not going to review the movies, but I'm going to try to talk a little bit about the maintenance of continuously welded rail, which is a big deal, particularly, well, it's a big deal throughout the world, but it becomes a big deal in places like Israel because of the temperatures that you reach and because of the generally warm weather that you have. Okay, so just to get things started, and again, I'm not going to spend a lot of time on it. There was a major track buckling derailment on Amtrak in Florida back in 2002. Like many track buckling derailments, it happens in the middle of the afternoon in the spring. Unlike the normal expectation is that you get most of your track buckling in the hottest day of the summer. Very often we find that we get the most track buckles in the spring because what happens is you've just gone through a winter cycle. People have done maintenance and they haven't readjusted the track to take into account the proper temperature for the laying the welded rail, and it's very common to have derailments in the spring or early summer. And 5 o'clock in the summer on a spring or summer day is still pretty much in the heat of the day. This particular train was called an auto train, which means it was a passengers, plus it also carried automobiles and cars in the back, but most of the cars that derailed and that got damaged were passenger cars. You can see it was a pretty messy derailment. Again, the fatalities were in this overturned sleeper car. As we talked about before, when a car goes over the side, that's when you get most of the injuries. If the car stays upright, you get fewer injuries. Track buckle, this is what we're talking about, a lateral misalignment of the track due to high thermal forces. I'm going to come back to this after we talk a little bit about CWR, about what were the issues involved, but the main issue was maintenance procedures and maintaining the proper neutral temperature of the rail and any maintenance that was done in the track. That was the big issue here. Everything else was sort of secondary issues, had more to do with what happened after the derailment. So in this particular case, and we're going to talk about all these things, rail temperature control, restraint of the CWR, both lateral and longitudinal, and maintenance of CWR. Those were the big three issues that came out of this accident. So let's start off with what's continuously welded rail. Well, there are all sorts of definitions out there. One of the more commonly accepted definitions is rail welded together in lengths greater than 120 meters. That's a pretty common definition you see around the world, but it really doesn't make much of a difference. It's whenever you start welding rail together. In fact, we're at the point now where we can roll rail in 100-meter lengths. As you saw from the movie I showed you earlier in the class. Now, getting hoarse from talking. Can you all hear me okay? Should I put a microphone on?
No, it's okay.
You can hear me? Okay. If my voice starts to fail, let me know when I can switch to a microphone. Okay, so given the fact that CWR is a pain in the neck to maintain, which it is, why do we want it? Well, continuously welded rail gives us longer rail life. Why? Because if I don't have welded rail, I have joints. And I have joints, I have a lot more maintenance and failure and a lot more problems. Joint defects are the most common types of defects in jointed track. Rail end batter, which I showed you all sorts of nice pictures of in a previous class, all happens on jointed rail. The life of the rail is significantly shorter for jointed rail. And given the price of rail is of the order of $400,000 to $500,000 a kilometer to replace material plus labor plus installation. And by the way, for metros, it's even more. Because metros are very expensive to replace rail. Having as long a life of rail as possible is a major advantage. And of course, joint maintenance is reduced, which is a big maintenance issue. Longer track life. Not only does joint cause problems with the rail, it reduces sleeper life, and as I showed you last week, it can show all sorts of geometry degradation. So you have track maintenance, you have sleeper maintenance. For example, you can't even put concrete sleepers under a joint. So let me say, you shouldn't put concrete sleepers under a joint because the concrete sleeves will be battered to pieces by the joints. You can only use concrete sleepers in welded rail. Wood sleepers you can use in joint, but their life is less. You have less signaling problems. You don't have to worry about playing around with bond wires and conductivity and track circuits connections at joints because the CWR is just a piece of rail. Less wear and tear of rolling stock. The same dynamic forces that forces track degradation also goes up into the rolling stock and causes degradation of the rolling stock. We're going to talk a lot about that in January when I come back. We're going to talk about dynamic loading up on the wheels and track and car body and things like that. But joints cause all sorts of maintenance. Smoother, quieter ride. You don't get the clickety-clack, clickety-clack, clickety-clack. Most of you are probably not old enough, but actually, and you probably didn't have the opportunity because Israel Railways didn't really have that much track. But in the olden days, when you took a train ride, you always constantly hear this clickety-clack, 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 and that was the wheels going over the joints. And you get a much smoother, quieter ride with welded rail. Better fuel efficiency, greater speeds because the smoother, quieter ride, better track geometry. It also permits heavier axle loads for those in the heavy axle load world. But there are some disadvantages, and they got to pay attention to them. They're susceptible to rail stresses that are called buckles or pull-aparts. We talked about that in one of the early classes. Thermal compressive forces can cause track buckles. Thermal tensile forces can cause pull-aparts. Difficult to detect a change in thermal force or a buildup of thermal force. Until things actually start to happen, it's almost impossible to detect. Rail must be maintained within a precise temperature range. You have restrictions on when you can do maintenance, what your neutral temperature has to be, how you replace rail defects. When you replace rail defects with CWR, you have to make sure that when you put your plug back in, you're at the right rail temperature. Times for maintenance are restricted. You can't do maintenance in very, very hot days. Certain class of rail maintenance, like tamping, are not permitted in very hot days. Plugs have to be welding. You're reporting. You have to keep very accurate record keeping because it's really critical to know what your neutral temperature is. There's an additional first cost because the cost of the welding and the cost of the extra ballast, but that's made up by the life cycle cost. Requires specialty equipment, particularly in the welding. And this says increased risk of derailment. That really is a part of buckles and pull aparts. I'm not sure I believe that because joints have their own increased risk of derailment due to joint failure. So that's probably a wash. Okay. So we already talked about the theory of expansion and contraction. I'm not going to go over that in any great detail. You have a piece of rail, it gets cooled, it contracts, it heats, it expands, except if I lock it in place. So if I lock this rail in place by welding it in place, if it gets cold, I get tension. If it gets hot, I get compression. Why? Because the rail here wants to contract and can't, so it's basically pulling on the edges and causing tension. And here it wants to expand and it can't, so I get compression. The rail temperature at which I lock that rail in is the neutral temperature or the force-free temperature. We talked about that previously. And the rail temperature at any given point in time is the temperature of the rail, which is approximately 20 degrees centigrade greater than the temperature of the air. 20 to 25 degrees centigrade greater. And that's if you're in the heat of the sun. So the formula for thermal expansion, we went over this in a previous class. The change in length is alpha, the coefficient of thermal expansion, change in temperature, times the length of that rail. I'm not going to go through the examples. We've went through this. You can look over this on your own if you like. Again, if you lock it in, it gets cold, you get tension, risk of pull apart. Lock it in and it gets hot, get compression, leads to buckle, which is our track buckle. A little bit more severe track buckle. Again,
Professor,
examples of track buckle. Yes.
Is there another option for CWR, for welded rail? Is there another option?
What do you mean? I don't understand the question.
Welded rail, we use welded rail in order to connect rails. Is there another option?
To connect rails?
Yes.
There is a third option. Well, you can use joints, which have a gap, which allow for expansion and contraction.
Mm-hmm.
You can weld it, or in very special cases, you can use expansion joints. So, for example,
expansion what?
Expansion joints.
Okay.
So an expansion joint is basically, I have a piece of rail here, and I have another piece of rail over here. So I have the track going to the expansion joint, I have the track going to the other expansion joint, and I literally have an overlap between my two ends. So I can actually expand or contract at these expansion joints. Where you'll see expansion joints often is on bridges, specifically very long bridges. I think I get to this a little bit later, but it's a very expensive, and this is a difficult to maintain option as well. So it's not commonly used. So the short answer to your question is right now you either have welded rail or you have jointed rail. There's no third choice. You can use expansion joints, but there's no real choice, third choice. Again, you can see your various buckle. You can see your string line over here. You can see the size of that buckle. You can see here the string line. You can see the size of that buckle. Okay, pull aparts. We talked about pull aparts. In this particular case, I think I showed you the slide before. This was this bolt that literally got, or this bolt maybe. Probably you should have had two bolts in here. You have two bolts on this side. You probably had two bolts on this side. So that means both these bolts sheared off. There's one of them sheared off. So once the bolt sheared off, so the tensile forces were high enough to shear off this bolt and then cause it to expand. So you see this can now move freely because there's nothing holding this any longer. So the force-free temperature, as I indicated, is a temperature in which the rail is completely free of internal forces. Usually, when you lay rail initially, the force-free temperature is the laying temperature of the rail. So if you lay the rail at 30 degrees C, the force-free temperature is originally 30 degrees C, but over time, that force-free temperature is going to decrease, and you usually don't know what it decreases to. And to try to find out what the force-free temperature becomes a really difficult problem. It's possible to find out, but it's a very difficult process to use. So again, I'm going to skip through these problems. You can go through them at your leisure, but I think we went through some of these already, so I'm not going to spend a lot of time. I really want to get into maintenance of CWR. Force, again, is EA alpha delta T. E is the modulus of elasticity. A is the cross-section of the rail. Alpha is the coefficient of thermal expansion. Delta T is the difference between the rail temperature and the force-free temperature. So delta T is equal to temperature of the rail minus temperature force-free. And again, you should have all had this before. I've gone through this before. And rail force, again, you can see can generate very, very significant forces. Here, a 50 degrees C temperature change will give you 100 tons per rail. So if you're on a bridge with 4 rails, that's 400 tons. Again, track buckle. Okay, so let's talk a little bit about track buckling and a little bit about buckling theory. Why? So you can understand the mechanism behind track buckling. Basically, what happens, let's see if I have the next slide here. Okay, so I have a piece of welded rail with, let's say I have a couple of joints in between. So let's say this is 1,000 meters for argument's sake. So a kilometer. And so this end here is about 20 meters. And this end here is about 20 meters. And in between is about 960 meters. So this end is free, so there's no force in there. It builds up the force because each fastener has longitudinal restraint. So each sleeper takes a little bit of longitudinal force until I get to my maximum force, which is EA alpha delta T. And then my track, most of my 1,000 kilometers of track here has this EA alpha delta T of longitudinal force. Okay. What happens? So this is a plot that shows my increased delta T. So everything now is delta T. Every time we think in terms of track buckling or track pull apart, the important temperature is not the actual temperature itself, either the rail or the ambient. It's the difference in temperature between the rail temperature and the force-free temperature, delta T. So as delta T increases, I have the potential of the track popping sideways. In fact, in what's called Classer-Euler buckling, which is if you just have a column and you keep loading your column, what happens with classical buckling is you keep increasing your longitudinal force, which in this case is EA alpha delta T, until you get this critical point, and then it buckles out sideways. So this is load, this is deflection. So here it's buckle out sideways. This is the deflection equals 0 point. In railroad track, it's a little bit more complex because what happens is that as it reaches this first level delta C sub L, So, okay. So what I have is I have three states of buckling in the track. If my delta T is less than delta T sub L, it will never buckle. It's always stable. So I always have to have a delta T greater than delta T sub L. And we'll talk a little bit about what that value is in a moment. But it varies depending on my track structure and the amount of ballast and the kind of sleepers I have. So there's no one number here. Between delta T sub L and delta T sub 0, there is an alternate, there's an unstable and stable state. So I can have what's called snap through buckling. I can go through here and then my track can buckle out. Remember that movie that showed the track and then all of a sudden it just kicked out? Well, that's what happens here. You go through and you get the snap through buckling, and it's between delta T sub L and delta T sub 0. And in this zone, there's a probability or a risk of buckling, but there's no guarantee of buckling. In this zone, greater than delta T sub 0, the track will buckle. So I have a zone where I never buckle, a zone where I will buckle, and a zone where I might buckle, depending on the total energy involved in the system. Those are the three states that we're talking about. So once I buckle, remember my constant longitudinal force? In my buckle, because I've now expanded, what happens to my force? My force decreases, right? Because I've released some of the force. Not all of the force, but some of the force. So my longitudinal force in the buckling zone is less than my longitudinal force out here, which is still EA alpha delta T over here and over here. And then I have a transition zone where I go between the two. Now, now it's really, really important to remember that when I buckle, I still have some force in there. Why? Because let's say you have a maintenance crew and you're going out there and you're trying to fix that buckle. And so the first thing you got to do is you got to cut rail out. Well, if you go in there fat, dumb, and stupid and cut that rail because you got to cut the rail out and there's a longitudinal force in there, that rail is going to whip around and going to hit maintenance workers and probably kill them, because rail is a pretty rigid, strong component. 60 kilogram rail is 60 kilograms per meter. And you're dealing with a couple of, maybe with 100 meters of track here. So you're dealing with a ton of rail bouncing around. So there are a lot of precautions that you have to take. Again, I'm not going to get into all of the maintenance issues here, but I do want to point out to you that even when you buckle, you have some residual longitudinal force in that rail. So even in this situation, if you try to come in there and cut the rail here and here, you got to do it real carefully to make sure that rail doesn't cut it, that doesn't move on you. Track buckling can be either symmetrical or asymmetrical. By the way, a good reference to this, I think I've mentioned it. There's a textbook by Arnold Kerr, not 1978, I think it's 2005, called A Railroad Track, Fundamentals of Railroad Track Engineering by Arnold Kerr. I think in the very first class I gave it to you. In fact, I gave it to you when we talked about beam and elastic foundation analysis too. When we talked about beam and elastic foundation analysis, I actually gave you a picture of the book. He also does a wonderful job in talking about track buckling.
Alan, sorry, a question.
Yeah.
About the cutting the rail.
Yes.
I need to wait until the temperature is lower and then to do it, right?
Well, at that point in time, you can, but usually you never cut the rail in the heat of the day. Yeah, right. You don't want to cut the rail in the heat of the day. You want to wait till the temperature goes down.
And then I can cut it.
What?
I can wait to the night and then I can cut it.
If you have that luxury, yes, that would be better.
Okay.
But you always have to treat the rail as if there's some force in it.
Even
You always
it
have to
got,
respect that
even,
rail.
even it got to free force temperature?
If you know what the force-free temperature is. But the odds are it buckled because you didn't know what the force-free temperature is because it changed from when you laid it. That's one of the problems with CWR. You can lay the rail at a given force-free temperature, but it can change, and it usually goes down. So if you lay it in 30 degrees C and you come back maybe 3 years or 4 years later, it can be at 25 degrees C or it could be at 20 degrees C, and you don't know. That's why it buckled, because the change in temperature was more than you thought it was.
I understand. Thank you.
So you can see the two modes of buckling, symmetrical and asymmetrical. Here's a nice picture of them. This is a symmetrical mode. This is an asymmetrical mode. They both cause derailments. Pull aparts, we talked about it previously. I'm not going to spend a lot of time on it. Again, it's due to the change in temperature. Here's an example of a pull apart away from a joint. Now, I'll tell you, pull aparts can happen if I have a small defect in the rail. Because the defect, of course, reduces the cross-sectional area and increases the stresses. So it's not uncommon if you get a pull apart, you go in there and look at it, there's a defect in the rail. Another thing that happens is when you're doing ultrasonic testing in the winter, when the rail is in tensile stress, you're actually going to find more defects than you do in summer. It's a statistic that we've seen time and time and time again. And the reason is in the winter, the rail is in tension and it's really pulling apart the rail internally and it's opening up the defect to ultrasonic inspection. Whereas in the summer, when the rail's in compression, the defect is sort of being closed a little bit. And so it's a little bit harder to find in the summer. There's a pull apart and joint. I showed you this picture already. If you have a pull apart, yes, then the force goes all the way down to 0. Because once I have a pull apart, once this is moving, or once this is moving and opened up, then I have no more force here. So it's usually no problem to do a cut here and here because there's very small force there, unlike a buckle. That's what we see over here. After a pull apart, the longitudinal force goes all the way down to 0. Again, I'm not going to go through this. This is an example of the force here. You can see this is a calculation, and we calculated about an 85-ton longitudinal force due to a temperature change. What was the temperature change? About 38 degrees C. One of the places where we also see pull apart problems is places where there's some sort of damage to the rail. So here, this is a case where I had a pull apart and girder rail. This is an interesting case, so I'm going to mention it. So I'll tell you what you should never, never, never do. Okay, so this is a Metro, Phoenix, Arizona. I was actually called in on this one as well. They had 9 pull aparts within a month. It was all in the winter, of course, because that's when you have coldest weather, right? 8 of the locations, so this was the girder rail. It was a RI 52. I think it was an RI 59 section, if I remember correctly here. Now you can see they all occurred within really a month of each other. And you can see there was some pretty big separation. So this is what, 7 inches is 180 millimeters, 180 millimeter pull apart. Now, about 70% of these pull aparts happened at a place where the Metro wanted to torch cut some drainage holes into the girder rail. and they used a torch. And remember, I said this in an earlier presentation, you never, never, never torch cut anything in the rail because you generate such a high stress concentration factor with the torch cuts that you're going to fail. Plus, you change the steel. You introduce a residual stress due to the heating of the torch. So you have a double whammy. You have a very rough surface, which has a stress concentration, and you have a metallurgical change as well. In this particular case, they torch cut a hole in not all of them, but I think about 70% of them, and they failed there. In the other ones, they did not torch cut a hole, and it just failed normally because of the situation. This is where they didn't torch to cut the hole. I think this is, I think, where you just had a pull apart. So what happened here is that the original spec had the rail being laid at between 50 and 60 degrees Celsius, centigrade. Oh, I'm not going to go through all the analysis. In reality, what happened, they laid it at about, there was a very hot spell. No, I'm sorry, I take that back. The spec originally was to lay between 40 and 50 degrees, and they ended up laying it between 50 and 60 degrees. And so in the winter, they had a temperature change of 55 degrees centigrade, delta T. So they generated about a thermal stress of about 90 megapascals, just due to the thermal stresses alone. So what happened here is that there was a stress concentration. I'm not going to go through the discussion. There was a stress concentration of about 5 due to the, in this particular case, the torch cutting. And so all of a sudden the stresses, the actual stresses went up from about 90 megapascals up to about 450 megapascals, which were actually below the endurance limit, sorry, below the ultimate strength of that rail, and though they failed. Now, as I mentioned, the longitudinal the force-free temperature changes with time. There are some techniques that are out there, mostly involving putting strain gauges on the web of the rail to monitor the longitudinal forces. The problem is they have to be installed at 0 stress. So that means you have to cut the rail, install the measuring systems, and then reinstall the rail. So they're fairly difficult to do. There is a system called the verse. Where you don't have to cut the rail and you can measure the longitudinal force. What the verse system does, so I'm looking at the side of my track. So here are my sleepers, my rail. If I disconnect about 10 meters of rail from the sleeper, so I remove roughly 10 meters of rail from the fasteners, the verse system pulls the rail up and measures the deflection. And by looking at the relationship between the rail size, the amount of force it goes to pull up the rail, and the deflection, it can actually calculate the force-free temperature or the neutral temperature of the rail. So that's a technique that is also that is out there commercially. This is one technique, this is the other. Okay. So I indicated the fact that, so if we have the buckling curve, the delta T versus deflection curve, so this is deflection versus 0. So I indicated there's a T sub L, the delta T sub L, the change in temperature in which buckling will never occur. How do I calculate that? Well, it's a fairly complex calculation, but what's really important is what it depends on. It depends on my ballast condition, the lateral resistance of my sleeper, which is a function of the shoulder width, the cribs, then the filled number of cribs, and the ballast in the base of the sleeper. My longitudinal resistance to the sleeper, which is a function of the cribs and the ballast ridge. Did everybody remember what a crib is? Crib is the space between sleepers. I have two different sleepers. This area is my crib. If it doesn't have ballast in it, then I have reduced lateral and longitudinal resistance, and and my delta T sub L goes down. My risk of buckling increases. So my delta T sub L is a function of my ballast resistance, lateral and longitudinal, my rail section, my fastener restraints, the type of fasteners I have, the type and weight of sleepers. Concrete sleepers weigh about 3 times the weight of timber sleepers. So they're actually more resistant to buckling than timber sleepers. The use of end plates at the end of my sleeper to give me increased ballast resistance. So if I have shoulders over here, and I put an end plate in the end of the sleeper, that'll give me increased lateral resistance. All these affect my delta T sub L, my lateral resistance. Factors that affect my pull apart strength, they're a little bit more limited. There's the rail section and material, the strength of my joints and fasteners, and also my longitudinal restraint of my fasteners all affect my pull apart strength. So I have longitudinal resistance effect, which is the fasteners and the ballast I have the lateral resistance effect. Lateral resistance is a function of my shoulders, my cribs, the ballast underneath my sleepers, the type of fasteners that I have, and things like the type of sleepers I have. Here's concrete sleepers. So this is a really good, well-maintained ballast section with good lateral and longitudinal resistance. Another example. Okay. There are actually techniques for measuring the lateral and longitudinal resistance of the track. Basically, what the most common method is what's called the single tie push test, where I take a sleeper, disconnect it from the rail, apply a load along the axis of the sleeper and track, and I measure the load and the displacement, and I get a load displacement curve as I see here. The lateral resistance is defined as the asymptote of this curve. So this is the load displacement curve laterally that I get, and this is the asymptote. So in this particular sleeper design, the resistance is about 800 kilograms per meter, lateral resistance. Longitudinal resistance, I would disconnect the sleeper and load it longitudinally. And again, I get a load displacement curves, and I define the longitudinal resistance by this asymptote. We talked about fastener longitudinal restraints. I think that should be covered elsewhere. Generally speaking, fastener longitudinal restraints have the order of 11 to 15 kilonewtons per rail seat. So again, remember, this is how you build up your longitudinal resistance. If I have a joint here, then I have 0 longitudinal force here, and my longitudinal force builds up this way, but actually, here's my rail. Here are my sleepers. My longitudinal force, actually, if I want to plot my longitudinal force, it's actually going to look like this. I have 0 out here. My first fastening system, about 11 to 15 kilonewtons per rail seat. My second one, so now I'm up to 20 to 30 kilonewtons. Now I'm up to 40 to 50 kilonewtons. Now I'm up to 70 to 100 kilonewtons. So By the time I go about 50 to 60 meters, I can generate a longitudinal force of 110 tons. So 50 meters down the track, I have my full longitudinal force, which could be like about 100 tons. Pull apart gap is a function of the change in temperature and the resistance as well. You can actually calculate the gap by looking at the delta L, calculating delta L as a function of your restrained length. I'm going to skip some of these because I don't have enough time. I'm running out of time. Track lateral resistance. Maximum benefit of track lateral resistance, which is one of your key criteria to buckling, is adequate tie-in, shoulder, bottom, and crib resistance. That's probably the single most important thing you really want to do. You want shoulders to be of the order of 300 to 450 millimeters. Minimum shoulder width of 300 millimeters. Welded rail should never have shoulders less than 300 millimeters. Again, remember, shoulders is the ballast at the end of the sleeper. Minimum should be 300 millimeters, never less. And well consolidated ballast. Now, what happens if I come in and I tamp my ballast? If my benefit comes from good ballast to holding my sleeper in, what happens if I tamp my ballast? If I tamp my ballast, I can reduce my lateral resistance by about 30 to 50%. So here's a good example. This is an example of lateral resistance. So here's very well consolidated, really good ballast, 300 millimeter shoulder, 5-degree curve. My lateral resistance is between 14 and 17 kilonewtons per meter. I take the same track. Where are we? There we go. I take my same track. Well, this is a slag ballast. So let me compare apples and apples. Okay, so here's a slag ballast, which is a poorer quality ballast, about only 0.1 MGT consolidation. Again, 300 millimeter shoulders. My lateral resistance is about 10 kilonewtons per millimeter. But if I just tamp that track, my lateral resistance drops down to about 5 kilonewtons per millimeter. So it drops to about half of the consolidated value and a third of the value of really good ballast well consolidated. So one of the issues I have with maintaining CWR track is I have to be really careful what happens when I maintain my track. If I do tamping, I do maintenance, and I reduce the lateral resistance of my track structure. Here's another example. This is actually a better example. I should have used this one earlier. This is my load deflection curve for concrete sleepers, well consolidated before maintenance. And this is the same track after tamping. And again, you see the lateral resistance drops by a factor of 2.5. Curvature and alignment. High curvature track are more buckling prone than lower curvature track. Why? Because I don't have the curve here, but basically, if I have that, remember this curve I had over here with some T-sub-L? If I have a high curvature track with an alignment issue, my theoretical curve actually changes, and it changes to look like this. So I now, whereas T sub L was over here, I have a lower T sub L for a curvature track. So curvature tracks have higher risk of buckling than tangent track. So it's even more important to maintain good, good level of consolidation.
What is a prone, please?
What's
Buckling
one
prone.
Say again.
Buckling prone. Buckling prone.
Buckling
Next.
from thermal compressive forces due to temperature increase. And see,
Okay. Okay.
this is my temperature increase in welded rail track.
Okay.
Okay, so care must be taken to avoid disturbing lateral track strengthening. So I said, remember I said there was limitations on when you can do maintenance. If you have CWR track, you can't do tamping in hot weather. Because if you disturb the track in very hot weather, when you have a high compressive force, you can buckle. And even after you disturb the track, you need to allow the ballast to consolidate. How do you consolidate ballast? You consolidate ballast by running trains over it. You can also use an external consolidator. There are machines that bring plates down on the top of the ballast and vibrate them. So in some railways, they actually use these consolidators behind the tamping or a surfacing gang to increase the lateral resistance of the ballast. But the most common technique is to slow trains down. So for example, here's a railroad standard I took from one major railroad in the US that basically says that if I had to replace ties, and I'm talking about cool weather, you know, I need to wait 48 hours of traffic before I allow my track to go to normal speed. I'm reduced to 50 kilometers per hour for 2 days until I run speed, until I get speed. Other standards go to about a certain amount of tonnage, MGT. So let's go back to the Amtrak derailment, which I think I'm going to sort of end over here because I want to make this point because it's really point. What happened? Okay, so this derailment happened in April 2002. It turned out that between October 2001 and April 2002, there was an extensive amount of maintenance. Just between January 2001 and April 2002, the track was resurfaced 16 times without adjusting the neutral rail. So they actually, and here's a picture of the ballast. Notice there's no shoulder ballast. Notice the sleepers ends are completely exposed. Also, there's no crib ballast. So this track was extremely weakened. Another picture. You see the ballast is actually sloping off the end of this sleepers. Here you can actually see a gap between the sleeper and the ballast, showing that this curve was actually moving in and out, which happens in the summer and winter. Because you have thermal expansion and contraction, you can actually move the curve in and out with changes in seasons. And again, that can create a gap in the ballast, which reduces lateral resistance. And the CSX that rail was supposed to be at about 40 degrees C. And we think it was significantly lower because of that movement. In fact, this was the curve where the buckle took place, and you can see it took place in April, so it took place in 4/2002. And you can see they actually did maintenance as recent as March 2002 in this zone, right in the zone of the buckle. So you got to be really, really, really careful. There was another problem here as well. The train engineer saw the buckle ahead of him and he initiated braking action, which means he put a longitudinal compressive wave into the track and widened the defect. So that was a secondary problem or a related problem. Okay, I'm going to stop here because I really can't give this justice. I recently gave a course to an American railroad on track buckling maintenance and standards, and it was basically an 8-hour course to cover the material I tried to jump through here in about an hour. So I just wanted to give you a feel for track buckling. Let me stop and see if there are any questions.
What is CSXT?
That's a railroad in the United States.
Okay.
That railroad has about 40,000 kilometers of track, roughly speaking. So it's a big railroad. It's about the same size as the French system. Any other questions? Okay, I'm going to stop sharing here, and we're sort of out of time. I'm going to give you a chance to ask any questions for the next 5-10 minutes you want. Also, feel free, as you study for the exam, feel free to email me. I've seen a couple of emails already. I'll get back to you in the next couple of days with answers to your questions. But as I said in the beginning, start off by looking at the problems I gave you on Moodle, the class problems. If you know that material, you should do well on the exam. There is other questions or other material. If you want to get I tell you, I don't get too many hundreds on my exams. I think if I get one a class, that's good. But I get a lot of between 80s, and I get a lot of 90s, and I get a lot more between 80s and 90s. I'd say probably 70 to 75% of the class gets over 80 in my exam. So I fully expect, and I hope everybody passes with good grades, and asking me questions, focus on the Moodle problems, and this is your chance to ask a few questions now. I know I covered a lot of material today. The good news is the stuff that I zipped through, I probably it will not be on the exam. I just wanted you to get a little bit of a knowledge behind this, because I want you to have a starting place if these issues come up, so you know where to start from. Silence. I've worn everybody out. I covered a lot of material today. I really did. I know I covered a lot of material today. So you're all tired. It's late by you. I'm wiped out because teaching 4 hours is very exhausting at my end too. So everybody, good luck. Well, good luck on the exam. Shana Tova. Have a good, happy, healthy, and sweet New Year. Shana Tova Mtuka. And may you all be inscribed in the book of life for a good, happy, healthy New Year.
Alan,
Thank you.
very much.
Thank you.
One question,
Yes.
small question, personal, not about the lecture. I wrote you in the beginning of the lesson. I was late by a few minutes.
Yes, you
Did you
did.
see my
I was going to send you a chat back. Today, Marina took attendance. So just send an email to Marina saying you were there.
Okay. Okay.
Just send an email to Marina directly, because she started the class and she took attendance today instead of me.
Okay.
So just send her an email.
Thank
Okay.
you. And right back at you with all the congratulations.
Say again.
And Shana Tova to you too.
Thank you. Thank you. Shana Tova, everybody.
Thank you.